Gigantic shadows drift beneath the ocean, casting doubt on the existence of Megalodon. Massive bite marks adorn whale bodies, hinting at fierce predators stalking the depths. Have we truly seen the last of Megalodon? Legends of oceanic giants persist, yet 95% of the ocean remains shrouded in mystery. Predators have concealed themselves in this abyss for eons. In the deep sea, size isn't everything. Even smaller creatures can become nightmares. Dive into the abyss and tell us where you're from. Welcome to the realm of deep sea sharks. As you descend, the monsters become increasingly surreal. The ocean's vastness continues to unveil its secrets. With advances in technology, we discover a growing list of shark species. In 2023 alone, 4 new species emerged, unveiling enigmatic predators lurking in the water. Two new types of six-gill saw sharks were documented, continuing a lineage with 6 gill slits, unlike most sharks today. One of the oddest finds is the demon cat shark from the ghost shark family, found off Western Australia's coast. It features glowing white eyes and uniquely shaped ribbed eggs. Measuring just 30 to 60 centimeters, it inhabits dim depths where sunlight cannot reach. Slightly deeper, the painted horn shark was confirmed as a new species after long confusion with the Heterodontous zebra. It measures 60 to 120 and has distinctive markings, helping scientists realize it was previously undescribed. In recent decades, the number of known shark species has climbed significantly. In the 1980s, only about 360 species were recognized. Today, we surpass 500, showcasing a 40% increase in just 40 years. Modern innovations, like unmanned submersibles and DNA analysis, have aided scientists in accessing previously unreachable areas. How many more species remain hidden in the shadows? For years, sharks have been labeled as cold-blooded predators lurking to hunt humans. However, this view is far from reality. Each year, roughly 60 shark-related incidents occur worldwide, with a remarkable low fatality rate. Meanwhile, millions of sharks are killed annually for their fins and liver oil. Sharks are not merely hunters, they are vital for maintaining marine ecosystem balance. Found in nearly all oceans, from shallow coastal waters to the abyss, sharks have witnessed Earth's evolution over millions of years. While dinosaurs faced extinction 66 million years ago, sharks adapted and thrived, making them one of the ocean's oldest survivors. In 2023, a 439 million-year-old shark fossil was unearthed in China, the oldest recorded. This finding enhances our understanding of shark evolution, hinting they may have existed even earlier than thought. It bolsters the theory that sharks could have predated the first bony fish, making them some of the oldest surviving lineages. Shark history traces back to the Ordovician period, around 450 million years ago, when their earliest ancestors roamed the oceans. At that time, life on land was sparse. Most organisms were evolving in aquatic environments. Approximately 420 million years ago, sharks diverged from primitive cartilaginous fish, one lineage evolving into chimeras found in deep waters, which we'll encounter later in this video. Around 195 million years ago, during the Jurassic period, the first modern shark group emerged, the Hexantiforms. Throughout the ages, sharks have developed remarkable traits, perfecting their predatory nature. Their bodies are crafted for speed and agility, while their jaws serve as sophisticated hunting tools. Unlike most fish with fixed jaws, sharks can extend and retract their jaws forward to capture prey. While sharks have evolved to thrive in various marine environments, their diversity expands continually. Some Hemicillium species can even walk using their fins over sand beds and coral reefs, propelling themselves without swimming. Beneath the moving waves and drifting plankton lies a world of fascinating sharks we will uncover. Around 200 meters deep, just past the continental shelf, the ocean transitions into darker waters where light fades, altering the environment drastically. This marks the boundary between lively, shallow waters and the mysterious deep sea, a world where only the most adapted creatures can endure. Beyond this point, light is inadequate for photosynthesis. Phytoplankton, integral to the oceanic food chain, struggle to flourish, leading to significant ecosystem shifts. Life flourishes on the surface with vibrant coral reefs, yet as you descend, the ocean transforms into a quieter, colder space, becoming more alien with depth. The ocean's division into layers is not a new concept. Western marine scientists studying the North Atlantic and Mediterranean first established deep-sea classifications based on their observations in vast continental shelves. Every region past the continental shelf is deemed deep sea, despite some inaccuracies worldwide. The first deep sea layer below this boundary is the mesopelagic zone, known as the twilight zone. Between 200 and 1,000 meters deep, only faint sunlight remains, barely enough for orientation, but insufficient for photosynthesis. Rare forms of seaweed can survive at around 295 meters, but few plant life persists beyond that. Below the twilight zone, the ocean plunges into total darkness. Between 1,000 and 4,000 meters lies the bathypelagic zone, or midnight zone. Here, there's no light, no plants, only creatures designed for eternal darkness. As you plunge further into the abyss, you'll find the abyssal zone, which endures extreme conditions, immense pressure, and temperatures of just 2 to 3 degrees Celsius, with seemingly little to no life. Yet even in this harsh realm, life finds a way to exist. The Dumbo octopus drifts through icy waters with its ear-like fins. Even sea cucumbers, resembling sausages, glide along the ocean floor, playing crucial roles in the food chain. Although it may seem lifeless, this realm is not devoid of life. It merely operates differently than the upper layers. Beyond the abyssal zone lies the ocean's deepest trenches, untouched by sunlight for ages. The hedopelagic zone, at depths beyond 6,000 meters, exists exclusively within deep-sea trenches like the Mariana Trench, reaching a staggering depth of 10,135 meters. Here, pressures exceed 1,000 times that of the surface, forming an environment nearly unreachable for humans. Creatures such as the snailfish have adapted to endure these extreme conditions, recorded at astonishing depths of 8,136 meters. Life in this zone relies on energy from hydrothermal vents, where minerals-rich hot springs nourish thriving bacteria and extremophiles, establishing a distinct food chain separate from the sunlit surface world. From sunlit shallow waters to the ocean's deepest layers, sharks have adjusted to survive throughout every ocean corner. Each depth presents unique challenges, from strong currents and severe temperatures to complete darkness. These predators have evolved various traits to endure, making them one of the most versatile and diverse marine groups on Earth. The layers of the deep sea hold more than just mysteries waiting to be revealed. They exemplify life's remarkable ability to adapt. Unlike terrestrial barriers, marine animals navigate without fixed depth limitations. Various species thrive in both shallow and deep waters. Sperm whales dive into the twilight zone for giant squid, while great white sharks frequently descend nearly 200 meters for sustenance. Predators, bioluminescent creatures, and the ocean's weirdest beings exist beyond the numerical boundaries we often impose. Sunlight pierces the deep blue waters, where waves flow endlessly and currents transport countless small fish. Here, the apex predators of the open ocean eternally lurk. Their physiology has evolved to thrive in this vast world where speed, vision, and sensitivity define the survival stakes. Sharks inhabiting this layer possess sleek, elongated bodies that glide swifter through vigorous currents while conserving energy. The blue shark, one of the most widespread species, can be found across major oceans, from the Atlantic and Pacific to the Indian Ocean. It resides in the epipelagic zone, from the surface down to about 200 meters, where sunlight and abundant food are abundant. The blue shark's slender structure allows for remarkable speed and efficiency, reaching up to 60 kilometers per hour. Its large eyes can spot prey from afar, and its keen sense of smell detects blood in water even at minuscule concentrations. Though it might not be the strongest predator, its speed and adaptability make it proficient at seizing opportunities. Unlike regional sharks, the blue shark is an ocean wanderer, migrating thousands of kilometers annually while crossing oceans from temperate to tropical zones, following currents in search of food and breeding grounds. The short-fin mako shark dashes through water like a silver flash. It is unrivaled in speed, capable of reaching 74 kilometers per hour, crowned the fastest shark. With an average length of 2.5 meters, its sleek body and large pectoral fins enable efficient movement through water, reducing drag. Its skin is more than mere protection. Intricate micro-ridges improve water flow, enhancing swimming speed. Combining a streamlined shape, powerful muscles, and temperature regulation, it stands as one of the most effective ocean predators. The shortfin mako primarily resides in the epipelagic zone, down to around 500 meters, where light supports visibility. It preys on skipjack, tuna, swordfish, and occasionally smaller sharks. With sharp eyesight and a remarkable sense of smell, it detects prey remotely and swiftly closes the gap. This glimpse of the ocean's upper layers illustrates how astonishing its deeper waters truly are. Ocean depth classifications don't rigidly dictate shark habitats. Some shallow species can plunge deep, while others from the deep sea may rise to hunt. This behavior may link to the deep scattering layer, parallel to the great terrestrial migrations. Discovered during World War II, the deep scattering layer was identified when naval vessels used sonar to find submarines. They encountered an acoustic reflecting layer several hundred meters down, moving over time. Initially assumed to be a false signal, further investigations revealed billions of marine organisms migrating together, forming a monumental sonar reflecting layer. The deep scattering layer includes mesopelagic fish, such as lanternfish, small yet bioluminescent creatures, along with squid, krill, and other plankton. Beneath the ocean's dim light, they create a dense layer spanning the world's oceans, not merely housing tiny creatures, but providing critical food for larger fish, sharks, and seabirds.
This layer sinks to 300 or 500 meters by day, avoiding predators like tuna, swordfish, and dolphins above. At night, darkness grants them safe passage toward the surface to feed, facilitating one of Earth's largest vertical migrations across oceans daily. At Seal Island, off South Africa's coast, great white sharks exhibit breaching, leaping from the water to attack seals. This strike employs explosive speed from below, generating enough force to launch prey into the air. Their teeth are among the ocean's most potent hunting tools, with hundreds of serrated razor-sharp teeth, some reaching 7 centimeters long. Each tooth is designed to tear flesh with ease, and their bite force can reach 18,000 newtons. Remarkably, their teeth are continuously replaced. Each broken tooth is swiftly supplanted with a new one, ensuring they remain equipped for hunting. Great white sharks aren't just solitary hunters. They exhibit complex social behaviors when hunting in groups, often establishing hierarchies with more dominant individuals. They showcase learning abilities and adaptability, refining hunting strategies based on past experiences, a rarity among sharks. Most hunts occur near the surface, but great whites can also dive to depths of 1,200 meters, driven by hunting and physiological adjustments. Unlike many sharks reliant on vision, they possess a sophisticated electroreceptor system, the ampullae of Lorenzini, allowing them to detect bioelectric fields from prey, even in darkness. This capability lets them find creatures buried on the ocean floor or obscured in black waters. Great white sharks dive deep to exploit abundant food sources in the deep scattering layer, which contains mesopelagic fish, squid, krill, and plankton. They track this vertical migration, waiting for prime opportunities to hunt, particularly during the day-night transition when prey is vulnerable. Tagged data indicates cyclical deep dives during long migrations. These dives regulate body temperature as they navigate through varying water temperatures. Importantly, these depths also help them evade one of the ocean's greatest predators, orcas. Many shallow sharks occasionally dive deep to access the deep scattering layer's resources, with only a few doing it as frequently as the scalloped hammerhead shark. Their broad heads enhance vision and host ampullae of Lorenzini, allowing it to sense electricity from prey, even in pitch-black waters. In total darkness, it perceives faint electrical signals from the nervous systems of its targets. The deep dives might also aid body temperature regulation. Swimming into colder depths helps lower their body temperature, conserving energy. In certain instances, this behavior may assist migration, optimizing usage of ocean currents to find new hunting grounds. The whale shark, the planet's largest fish and one of the deepest diving shark species, competes in the deep diving stakes. Reaching lengths of up to 18 meters and weighing over 20 tons, it glides through the ocean like a cloud. Modern trackers report astonishing dives by whale sharks reaching 1,912 meters. This behavior might be an essential survival tactic. At these depths, the deep scattering layer remains active, transporting countless squid and small fish, supplementing the plankton they consume daily. Monitoring the deep scattering layer's movements grants access to richer feeding grounds, even in plankton-scarce areas. Whale sharks swim with their mouths open like giant vacuums, sucking in water. Specialized gill rakers filter food particles from the water, separating microscopic plankton before ejecting the filtered water. This low-energy feeding method ensures they gather enough sustenance for their immense bodies. Their ability to dive deep raises questions about how they manage pressure at nearly 2,000 meters below the surface. Unlike other sharks with active temperature regulation, whale sharks might rely on a complex system for adjusting to cold deep-sea waters. Transitioning between layers may also conserve energy, utilizing currents for efficient travel while avoiding competition. Moreover, whale sharks rank as one of the most far-ranging migratory species, traversing thousands of kilometers annually for plankton-rich feeding grounds. They seasonally appear in hotspots like offshore Mexico, the Philippines, and Ningaloo Reef in Australia. These migrations partially stem from feeding needs, but may also relate to reproduction, an enigma yet to be unraveled. Among organisms that follow the deep scattering layers rhythm, the megamouth shark stands out as one of the most enigmatic. Typically about 5.5 meters long with a soft body and slow, deliberate swimming, it's one of only 3 surviving filter-feeding shark species, alongside the whale shark and basking shark. Discovered in 1976 by chance when one got caught in a U.S. Navy anchor near Hawaii, no one knew it existed before that encounter. Yet, neither the whale shark nor megamouth holds the title for being the most intimidating predator of the deep scattering layer. Perhaps the most peculiar is the cookie cutter shark, a small species measuring 42 to 56 centimeters, known for leaving horrifying bite marks, even more disturbing than giant sharks. Its body features thousands of photophores, emitting a faint green glow that camouflages it, rendering it nearly invisible. Yet, beneath its throat and gill slits, a distinctive dark band creates the illusion of a smaller creature gliding in the ocean. When inquisitive prey approach, the cookie-cutter shark strikes abruptly from below. The ocean extends beyond a vast surface. It conceals a hidden cosmos submerged in dark waters. Sharks, the sea's ancient predators, don't solely dominate shallow waters but venture into the abyss too. This behavior raises an important query. What drives them to plunge into depths where immense pressure and freezing temperatures await? Three hypotheses have emerged to explain this intriguing behavior. The first suggests navigation. Sharks don't depend solely on vision or smell. They also possess a magnetic sensing system through their ampullae of Lorenzini. Certain species may dive deeper for clearer geomagnetic signals to accurately orient themselves during extensive migrations spanning vast oceans. This ability may clarify why hammerhead sharks consistently dive deep before embarking on such migrations. The second theory revolves around energy conservation. Diving into chilly, deep waters allows sharks to utilize slow-moving ocean currents, easing swimming efforts and conserving energy for long distances. Basking and whale sharks have been recorded diving at great depths, potentially lingering there for extended durations to capitalize on slower water, minimizing movement costs. This strategy could be vital for long-distance migrant species, aiding energy preservation while crossing food-deficient territories. The final hypothesis pertains to thermoregulation. While most sharks are cold-blooded, certain types, such as the great white shark, maintain heat within their muscles, enhancing hunting efficacy. Spending excessive time near the warm surface may gain up excess body heat, leading them to dive into colder waters to regulate temperature and avoid overheating. Scalloped hammerheads have been observed closing their gills while diving into colder areas, helping conserve heat during prolonged deep water stays. Nevertheless, despite deep diving being a survival strategy, sharks face depth limits, even deep-sea residents. Unlike small bony fish, which can endure depths close to 8,000 meters, sharks are seldom found below 4,000 meters. This ceiling reflects not random chance, but physiological and ecological constraints that ancient predators grapple with. A major challenge for sharks diving deep is buoyancy. Unlike bony fish, sharks lack swim bladders for buoyancy control. Instead, they rely on their livers filled with squalene oil. This oil provides neutral buoyancy in seawater, but its effectiveness wanes under pressure. At extreme depths, the reliance on squalene diminishes, compelling sharks to expend more energy to maintain position. Faced with choosing to swim in food-scarce regions or remain in lower pressure zones, sharks appear to favor the latter. Beyond buoyancy issues, sharks encounter another hurdle: osmotic regulation, balancing water and salt levels within their bodies. Sharks don't excrete urine like other vertebrates. Instead, they retain urea in their tissues to match the osmotic balance with surrounding seawater. However, urea decomposes under pressure, forcing sharks to produce large quantities of trimethylamine oxide to protect their cells. At depths over 4,000 meters, the demand for trimethylamine oxide can surpass a shark's capacity to produce it, leading to biochemical instability. This may clarify why sharks struggle to endure extreme depths for long periods. Food scarcity proves another significant barrier, as sharks are high-energy predators, yet the environment below 4,000 meters is nutrient poor. At those depths, life primarily survives on organic debris or by consuming specialized deep-sea fish adapted to harsh conditions. Sharks, which need substantial food intake to maintain their size and mobility, would face challenges locating adequate sustenance in resource-deprived environments. This limitation illustrates that even ancient predators cannot escape the ocean's physical and biological laws. What do you believe awaits at the ocean's bottom? An undiscovered shark species or something far more chilling? The deep ocean represents unknown territory, constituting 98% of Earth's ocean volume, where sunlight only reaches a few water layers before vanishing completely. Beyond 200 meters, there's no light, no photosynthesis, nearly no plant life. To survive here, creatures must adapt to extreme conditions where food is sparse and ecological demands unyielding. As depth increases, water pressure escalates rapidly. At 3,700 meters, the pressure surpasses 400 times that at sea level. Most creatures in this realm lack air-filled cavities, enabling them to withstand the pressure's crushing force. Certain deep-sea sharks possess soft, flexible cartilage and less dense bodies than the sea surrounding them, maintaining agility despite extreme conditions. The temperature in these depths typically varies between 1 and 4 degrees Celsius, nearing freezing. Unlike surface-dwelling sharks like great whites, which generate muscle heat for efficient hunting, deep-sea sharks conserve energy by slowing their metabolism. They can endure lengthy periods without food, sometimes depending on sinking carcasses as their primary nutrient source. In deep waters, oxygen levels present another challenge. Many deep-sea shark species have more gill slits compared to their shallow water counterparts. They often adopt energy-efficient swimming patterns, remaining motionless rather than continually propelling themselves to maintain oxygen flow. Despite these survival challenges, deep-sea sharks account for nearly half of all known shark species, navigating depths rarely explored by humans, holding mysteries yet to be unveiled. They might not depend on speed or power, yet have existed for millions of years, silently residing in the ocean's depths. Deep-sea gigantism remains one of the greatest mysteries below the ocean surface. Shallow waters generally feature small creatures, compact and fast to evade predators. However, this principle breaks down in the deep ocean. There, deep-sea animals exhibit significantly larger sizes compared to their shallow water relatives. The giant isopod, resembling an oversized pill bug, can grow up to 50 centimeters, while shallow ones typically measure only a few centimeters. The giant squid, among the largest invertebrates, can stretch up to 13 meters, its tentacles reaching into the darkness to snag prey. What stimulates such enormous sizes in deep-sea animals? One popular theory links this to the cold, deep ocean, slowing metabolic processes and extending lifespans, allowing these creatures ample time to grow. In a food-scarce setting, larger bodies store more energy, helping them survive longer without nourishment. Another theory posits that predator pressure is less intense than in shallow environments. Without swift, high-energy predators like the great white or short-fin mako, deep-sea creatures can afford slower growth, ultimately achieving larger sizes. In this realm, survival hinges on endurance, resilience, and adaptation. Among the icy waters of the North Atlantic and Arctic Ocean, the Greenland shark vividly illustrates deep-sea gigantism. Reaching upwards of 7.3 meters and weighing more than 1,000 kilograms, it surpasses even the great white. Remarkably, the Greenland shark's lifespan is among nature's most awe-inspiring enigmas. Growing extremely slowly, it adds only about 1 centimeter per year, potentially living up to 500 years. Throughout its extensive existence, it has observed vast ocean changes, from ice ages to shifts in modern climates. At depths from 200 to 2,200 meters, where temperatures seldom rise above freezing, the Greenland shark has adapted by drastically slowing its metabolism. This strategy conserves energy while allowing survival in a world lacking food. Despite its slow pace, it remains an effective predator, consuming seals, large fish, and even moose that drift into the ocean. Researchers have discovered moose and polar bear remains in Greenland shark stomachs, highlighting its opportunistic scavenging nature as it capitalizes on food sources in a harsh environment. With its immense size and enigmatic existence, the Greenland shark stands as one of the deep ocean's greatest mysteries, often likened to an ancient phantom drifting through time, surviving centuries while mostly unknown. Perhaps this contributes to occasional mistaking of the Greenland shark for Megalodon, the giant prehistoric shark that became extinct around 3.6 million years ago. Approximately 23 million years ago, during the Neogene period, the ocean was ruled by one of the most significant predators to exist, Megalodon, the largest shark ever, dominating warm seas globally. Megalodon had no complete skeletons found, as, similar to most sharks, its structure was cartilaginous, hindering fossilization. Nevertheless, fossilized teeth, some up to 18 centimeters, have surfaced worldwide, from North and South American coastlines to Europe, Africa, and Australia. Based on these teeth, Scientists presume Megalodon measured between 15 to 20 meters, 3 times larger than a great white shark, making it appear juvenile by comparison. Yet its terrifying size was only one aspect of its menace. Megalodon's jaws held one of the most potent bite forces in the animal kingdom, with estimates ranging from 108,500 to 180,000 newtons, making it 10 times stronger than today's strongest predator, the saltwater crocodile. Its diet showed its apex predator status as it consumed massive prey. Fossilized bones from ancient whales, dolphins, and even giant turtles bore megalodon bite marks, confirming its place atop the food chain. Hidden in the ocean's deepest layers, the goblin shark seems like a remnant of prehistoric times. As one of the oldest surviving shark species, the goblin shark has largely remained unchanged since the Cretaceous period, over 125 million years ago, surviving many geological and climatic shifts throughout Earth's history. Although seldom sighted, it is not completely mysterious. Specimens have been reported globally, from Japan and Taiwan to the South African coast and the Gulf of Mexico. Despite these sightings, most of its life remains unexplored, generally inhabiting depths of up to 1,300 meters, where few exploration devices can penetrate. The goblin shark's skin appears pale pink, almost translucent in light, distinguishing it among deep-sea sharks. Blood vessels near its skin's surface create this unique hue. What truly distinguishes the goblin shark is its exceptional jaw structure. Unlike other sharks with fixed jaws, the goblin shark can extend its jaw forward like a spring-loaded trap, an extraordinary hunting adaptation. When prey ventures too close, its jaws snap shut with remarkable speed. Equally bizarre is the chimera, or ghost shark, which is neither a shark nor a bony fish, but belongs to an ancient lineage of cartilaginous fish that predate the dinosaurs. After more than 300 million years of evolution, it retains many primitive features, rendering it one of the most mysterious deep-sea creatures, though seldom seen. Chimera species are distributed worldwide, inhabiting depths from 200 meters to over 2,600 meters. In reality, humans represent the biggest danger, leading sharks toward extinction. Overfishing threatens more than a third of deep-sea shark species. The cosmetic and pharmaceutical industries aggressively harvest squalane, a valuable compound from deep-sea shark liver oil. The gulper shark faces heavy exploitation and steep population declines. Urgent intervention in unregulated deep-sea fishing is essential to preserve these ancient animals. They've endured for millions of years, surviving mass extinctions, yet may not withstand human impact. The deep ocean endures as one of Earth's greatest mysteries. Its inhabitants dazzle not just with their unusual natures or hunting prowess, but largely due to our ignorance surrounding their existence. Meanwhile, we unknowingly accelerate their extinction. Secrets remain to be unearthed in the deep sea. It's our duty to ensure these creatures continue to exist and tell their stories. To protect the ocean, substantial solutions are on the rise. Marine protected areas, MPAs, have expanded dramatically since 2000, increasing coverage over tenfold, now encompassing around 7.2% of the ocean, roughly over 26 million square kilometers. The Biodiversity and Ecosystem Services Network aids countries in implementing biodiversity conservation plans. Utilizing modern tech, from satellite tracking to AI-enabled monitoring, improves management and protection of critical marine areas. Public awareness plays a vital role in conservation efforts. Campaigns have cut plastic waste entering oceans while promoting alternatives to shark liver-derived squalane. You can join widespread conservation movements, signing petitions against shark overfishing and supporting marine protected areas. Our oceans are vital for survival, and only through collective action can marine ecosystems restore balance. Have you encountered the most unusual shark yet? Share your experiences or insights in the comments below, as they might inspire conservation movements and help protect endangered species.